I'm Anulewicz. This is my lab for Physics 2211, number 3, black hole. So this is a two-part lab. The first part is me to analyze the star's orbit around a black hole in order to determine the mass of the black hole, and then using that information, we need to find the initial velocity of a spaceship on a planet in order that the ship will leave the planet's surface without crashing into the planet or into the black hole. For this, the fundamental principles we use are Newton's universal law of gravitation, Newton's second law, and the momentum principle, as well as the position and velocity update formulas. And our results were that the mass of our black hole was 7.29071 times 10 to the 33 kilograms. The initial velocity needed to escape both the planet and the black hole is negative 4.1 times 10 to the 7th meters per second in the x direction, and 2.2 times 10 to the 6 meters per second in the y direction. The key equations used here are the universal law of gravitation, where G is Newton's gravitational constant, 6.67 times 10 to the negative 11th. M is the mass of the larger body, in this case the black hole, and M is the mass of the smaller, in this case the star, with the R being the distance between the two. We also have Newton's second law of momentum principle, which states that F net is equal to dp over dt, which is equal to the parallel and perpendicular components added together. So that means that the perpendicular plus parallel components of our force are equal to the perpendicular plus parallel components of our dp over dt. Finally, to find the mass of the black hole, we need to set F net equal to dp over dt, and then solve for the uppercase M, in which case we get the mass of the black hole is equal to dp over dt times r squared over the mass of the star times the gravitational constant. Next, we have the velocity and position update formulas, which are used to calculate the initial velocity of the spaceship as it leaves the planet. So for the first part of the lab, our initial conditions are the mass of the star is 2 times 10 to the 30 kilograms, our t initial is 0 seconds, our delta t is 1 day or 86,400 seconds, our gravitational constant is 6.67 times 10 to the negative 11th, and our radius between the two is just the magnitude of the star's position, because of how since the black hole is at the origin, we can just use where the star is relative to the origin or the black hole to find the distance between the two. So here is my glow strip code for the black hole. So first what we need to do is calculate the parallel and perpendicular components of dp over dt, since those are what we need to use to find the magnitude of dp over dt, which is plugged into our equation. And once both those are found, we're able to get F net and our dp over dt, and we plug that into our equation where the mass of the black hole is the magnitude of dp over dt times the magnitude of our star's position squared, which is our radius, over the mass of the star times g. And our results were that the mass of the black hole was 7.29071 times 10 to the 33 kilograms, which is the average of all of our attempts. Our F net was 7.4727 times 10 to the 28th, with the parallel components being 2.0799 times 10 to the 28th newtons, and the perpendicular being 7.1879 times 10 to the 28th newtons. Next, for the second part of our lab, to find the spaceship's initial velocity, our mass of the black hole is from the previous section, which is 7.29071 times 10 to the 33 kilograms. The mass of our planet is 9 times 10 to the 28th kilograms, and the mass of our ship is 7 times 10 to the 10th kilograms. Here's our glow strip code for the second part. What we have to do here is first we need to find the force acting on the black hole on the planet and the planet on the black hole, and the force on the ship on the planet in order to find the F net on the planet. And then we do the same thing for the ship, where we find the force of the black hole on the ship and the planet on the ship to find the F net on the ship. Using these, we can update the position and velocity using the position and velocity update formulas of both the planet and the ship to determine where they are in order to figure out what our initial velocity the ship needs so that A, won't crash into the planet based on its position, and B, won't crash into the black hole based on the force acting upon it. Our results were that in order to both not crash into the planet, whose orbit is seen in blue, as well as escape the black hole, which is dot, we can follow the path of our spaceship, as seen in purple, and we get that our initial ship speed in the x direction needs to be negative 4.1 times 10 to the 7th meters per second. Our initial ship speed in the y direction needs to be 2.2 times 10 to the 6 meters per second, and this will allow us to escape the black hole and not crash into the planet. So now we need to go into what does this mean for the first part, as in, are the parallel and perpendicular components of net force equal to dp over dt, and if not, why are they different? So, as we've shown, since dp over dt is equal to F net, the perpendicular and parallel components of F net are equal to those of dp over dt, which is proven in our key equation section in which we show this, as seen right here. What this means is that they're equal as well. However, in this case, it's easier to substitute dp over dt equals fg as opposed to F net equals fg, because by using dp over dt, we don't need to account for the mass of the black hole on that side, which allows for us to only have to calculate the lone uppercase M, on the FG side of the equation. And finally, what if we wanted our ship to instead enter an orbit around the black hole as opposed to escaping it? So for this, we would need the initial velocity of our ship to be that which allows for the momentum of the ship to be perpendicular to the net force on the ship, which means that as the ship travels, its velocity will be tangential to its orbital path around the black hole, creating said orbit. So if the orbit's going in a circle right here, and we have the velocity tangential to that, it'll keep following that orbit and go around the black hole. This being said, the velocity needs to be slightly less than the x velocity and slightly greater than the y velocity of the planet, so the two do not crash together. Thank you.